Hello, everyone.
Hello, doctor.
Sorry to be late, but please, guys, mute your microphone and send your webcam and let's start. Mute your microphone. Send your webcam and let's start. Quickly, please. All send the webcam. All send the webcam. Quickly. Quick, quick, quick. Huh? Guys, I need 15 cameras. I see. Huh? Okay, Tony, your camera. Yeah.
You didn't get it, doctor? I sent it.
I tried. Okay. Yeah, I got it now.
Okay.
Thanks.
No problem. Okay. Send again, Hannah. Okay. Okay. And Mariam. Okay, guys, we talked last time about the solubilization. Okay. And we finished about the micelles. Let's remember about this. How to increase solubility of a compound. وجيها. How to increase solubility of a compound. وجيها. Unmute.
I didn't attend the last lecture.
You didn't study it?
No.
Okay. So what about you, Salma? Salma, how to increase solubility of a compound? Micronization?
I didn't really focus on this.
Okay, guys, by micronization, which is that decreasing the particle size, grinding, that increase the surface area and increase the solubility of a compound. Other way that we can using co-solvent, and the co-solvent can help in increase polarity of the compound to the water, and this will increase the solubility of the compound in the water. And the third one, which is about the adjust of the pH, like that if the compound is acidic, we should to put it in alkaline media, and if it is alkaline, we should to put it in the acidic media to make it more ionizable, so it's more soluble. And the third one, or the third way, is that using of the surface active agent or surfactant, which can increase the solubility or the miscibility between two liquids, because it will decrease or break down the interfacial tension between the two immiscible liquids. And we talked about that the surface active agent have something called that HLP, hydrophilic lipophilic balance. The HLP, the hydrophilic lipophilic balance, help in what? Help in that it can used for increase or talking about or adjusting about that this surfactant is more solubilized for the hydrophilic or more solubilized for the hydrophobic drugs. That when we have huge HLP, this meaning that it has a more hydrophilicity. And if it has a low HLP, it has a high lipophilicity. Okay, and we said that we have major three types of the uh, surfactant: the ionic surfactant and non-ionic surfactant. The ionic surfactant, which is like that, the cationic or anionic surfactant, but the non-ionic, which don't have a charge in the hydrophilic group at the head. And that was the three ways of the solubility, or how to increase the solubility, and also that using the okay, micronization, changing in the pH co-solvency, and the solubilization by the solubilizing agent. And number 5, which we will give today, which we will start with it today, which is the complexation. That's very nice examples that I given you, which is very, very, very nice in the medicine. Nowadays, you can bring the betadine, which its generic name is polyvinyl pyrrolidine iodine complex. Okay, what about this? Let's say that if I bring iodine itself and put it as a solution, it has a bad solubility. The iodine has a bad solubility. And at the same moment, this iodine is more toxic to our organs. How nowadays we bring betadine and put it in surgeries, put it in the open surgeries, open tissues, and it does not make any toxicity, because the composition of the betadine is 10 to 15% of vinyl of the polyvinyl pyrrolidine PVB complexed with iodine. That is make a good complex solution. This solution will liberate the iodine slowly, and this liberation slowly of the iodine will make it toxic for microbial, but not toxic for our mammalian cells. So this is meaning what? This is meaning that I can, by the way, that we can complex between polyvinyl pyrrolidine plus the iodine. This complex will make slow liberation of iodine from this complex. And this slow liberation of iodine will be toxic amount for the microbial, and very, very, very minor amount to present in our body, so it's not toxic. So the toxicity here is decreased by this complex to our tissues, because the slow liberation of iodine from this complex.
Doctor, could you please repeat the last part, the complexation ones?
okay, that complexing of the BVB with the iodine to give BVB iodine, that is make it slowly liberation from the BVB of the iodine. And iodine, if I put iodine in your tissues, this will be more toxic for you. But slow liberation of the iodine from this BVBI, this is will leading to that minor amount, minor concentration that will released. And this minor concentration not toxic for us, but toxic for microbial. So when you put the BVBI on the surgeries, open surgeries, okay, on the open tissues, this will not affect in your tissues by toxicity, but will affecting in any microbe come to your tissues by be toxic for it.
How is the slow liberation? I mean, what's
because of the complex?
No, but okay. So what kind of I mean, okay.
قولي بالعربي.
No, يعني the راحت لي الهدرة. Sorry.
Okay. The complex, the benefit of the complex here, that this complex can dissociate from each other very, very slowly. So this will give the iodine very, very slowly. And the free iodine will be in a minor amount. This minor amount not affecting in our tissues, but affecting on the microbe. Okay, toxic for the microbe. About the formation of inclusion bonds or inclusion compounds. Look with me, guys, here about this. Okay, this figure in front of you. This figure is a polymer, but this polymer is very, very bad to be soluble in water. Why? Because this polymer is, as you see, it is look like that is not organized. So it is not easy to be soluble in water. So when you're using the inclusion compounds,
if something is not organized, it will be more soluble, right?
What, sorry?
When the compound is not organized, it will be more soluble.
You're talking about other thing. You're talking about the polymorphism. That's something about the compound itself. But we here talking about the polymer. Polymer is like that. This is a molecule, this is a molecule, this is a molecule with each other. This is a polymer. Okay? Let me tell كنار in Arabic. يا كنار، هنا بقول دوت بوليمر، يعني عديد الجزيئات. الجزيئات دي ملفوفه على بعض زي خيط متلعبك. كويس؟ الخيط المتلعبك ده ينفع يدوب كده؟ ما ينفعش، لازم يتفك الاول.
اوكي دكتور، شكرا.
وصلت؟ لكن انت بتتكلم فيه ده حاجه ثانيه اسمها الجزيئات نفسها بتاعه المركب نفسه، بتاعه المولكيول نفسه مترتبه ازاي؟ الجزيئات جوه المولكيول نفسه. لكن ده انا هنا بقول لك مولكيول ومولكيول ومولكيول ومولكيول، يعني عاملين البوليمر. وصلت؟
نعم دكتور، نعم شكرا دكتور.
You're welcome. Okay, sorry guys. Here guys, when I say this polymer, as you see, is crossed with each other. Okay, and when the polymer crossed with each other, this is make it difficult to be soluble in the water. So I need to make it more organized like this. It's not crossed with each other. It's free with each other. Free like this. How to make this? By using the inclusion compounds. Inclusion compounds is something that help in opening this crossed figure to a free figure, very fine figure. And that is increase the solubility of the polymer. As we know, the polymer is good to be solubilized in the water, but when it become like this, organized like this, or that look like that, it is free like this. But if it's crossed with each other, it's difficult to be soluble in the water. So These like what? This is like what? The inclusion compounds or inclusion bodies, like what? Like beta cyclodextrin, which is the most common useful inclusion compounds that it's used for make this with the quercetin drug, and the nimodipine also can use the inclusion compound to be easier to be soluble, because nimodipine and quercetin present as a polymer, but this polymer is crossed with each other, so solubility is bad. So I can increase the solubility if we include it inside the beta cyclodextrin inclusion compounds. Another way to increase the solubility is a chemical modification. Like what? The chemical modification, like that we formulate the drug in a different salt structure. Look with me, guys, about this, about the penicillin V, for example. I can take the penicillin V. If I formulate it with a salt of potassium salt, it will be this yellow graph, which means that it reached to the highest concentration very, very quickly. So it can be absorbed and give the highest trough of the, or the highest concentration peak, okay, so quickly. And if you, that's because the salt of potassium salt is very, very easier to absorb it, very, very soluble to be absorbed. And if we make it as a calcium salt, it is less than the potassium. It will decrease the solubility and decrease the absorbability. And if we formulate as a free acid, it will be less than the calcium salt. And if you formulate it as a benzene penicillin, which is a benzene salt, it will be extended release, or it will be that extended action, okay, that will extend in the action, as you see, guys, like this.
Is it like extensilin, the last one? No?
Which one?
Extensilin, I don't know.
Which is benzene penicillin.
But they don't have it here, right? Or
don't have where?
in the United States?
Yeah, it's a generic that you're talking about. Yeah.
Oh,
yeah.
Okay.
That's in your country. Yeah. Like that, benzene penicillin can extend it in the duration of action. Due to that, the solubility of it is slowly, so it extends in the release. Using of metastable polymorphs that we talked about it in the polymorphism, if you remember, when we said chloramphenicol palmitate, the B form of chloramphenicol palmitate is the metastable form. And let's remember about this, guys. Henna.
Yes, sir.
Okay, can you tell me that B form of chloramphenicol palmitate is the more water soluble, which is the metastable? So can you tell me the B form or A, which has the higher energy?
Okay.
The B form or A, which has the higher energy? What's your
B form has higher
B
energy.
form is higher energy because the
B
higher
form.
energy, the higher energy, the higher solubility.
Yes.
Okay. Just a moment, guys, please. Okay, guys. So, guys, let's say that about this, which is about the metastable. If you remember that we said before, the metastable is the highest energy and is the highest solubility. Okay. About the partition coefficient, let's remember something from the past, from your undergraduate school. Okay, let's remember. When you have something like this, we call it as a flask, or sometimes we call it as the separating funnel. Okay, that you take some of the leaves of the plant, for example, some of flowers, something like this, you put inside, then you add water, and then you add chloroform, for example, as an organic solvent. So we have organic solvent and we have aqueous solvent, which is the water. Okay. After then you begin to shake, and we call this process as the procedure, we call it as the shaking flask, or the flask shaking. Okay, you begin to shake the flask for longer time, like 1 hour, shaking and so on. And after this, you take a sample from the organic solvent, you take a sample from the water. You're going to make a titration for the organic and titration for the water to get the concentration of this plant. For example, if we imagine this plant of papaverine, of the papavericin. So I will get the papaverine concentration in the organic solvent and the papaverine concentration in the in the organic solvent, and the papaverine concentration in the water solvent. Okay, when we look at both of them, okay, we after this going to get the partition coefficient. Partition coefficient is equal to the concentration in organic to the concentration in the water. Okay, so if the compound is more lipophilic, so P will be higher than 1. And if the compound is more hydrophilic, the partition coefficient will be less than 1. So from here we can deduce that the partition coefficient, which show the solubility of any compound, guys, should be between the water and the organic solvent. That may be higher in organic, maybe higher in water. That's well decided by the partition coefficient. And after we know the partition coefficient, we will decide if the compound is more lipophilic or more hydrophilic according to the partition coefficient. Okay, that's very important. After we know about the partition coefficient, what is the importance of partition coefficient? Okay, let me say, but concentrate with me because I will ask now. I will ask now, and I need you to concentrate with me, guys. Firstly, when I say the partition coefficient is high, before I talking about the application of the partition coefficient. When I say partition coefficient is high, this means more lipophilic. And more lipophilic, which is measure the lipophilic character of a molecule. And more lipophilic is higher potency or no in CNS?
It's higher.
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 Because it can
High.
Because it can
Cross it.
through
Blood-brain barrier.
Excellent. Excellent, guys. Okay, very good. You all answered. Okay, very, very nice. But we will see if you will answer what I will say or not in the after few minutes. Recovery of antibiotic from the fermentation we can deduce this by the partition coefficient. Extraction of drug from biological fluids like the blood, like from the saliva, like from the urine, and so on. Absorption of drug from dosage forms like the ointment, suppositories, transdermal patches. Study of distribution of flavoring oil between oil and water in emulsion. All of this is okay. And Mayer and Overton discovered the narcotic potency of an anesthesia can generally be predicted through the solubility in the oil. What's this? These people, Mayer and Overton, make something very, very, very nice, which is what? That these people begin to explaining about let's disappear. Okay. Okay, let's make it like this. Okay, Mayer and Overton make what? They begin to explaining that the potency of anesthesia, which can go through the brain, the blood-brain barrier, is very good according to the partition coefficient. So if you have today, for example, if I have today a new drug, very, very new drug, I didn't use it with human till now, I can expect the potency of the drug according to this line. That if we say the partition coefficient will be, for example, 7, like here. So I will look from 7, okay, like this, and I will decide this will be that at here, which is about 0.6, for example, as a potency. Without I use it with human, this line can let us detect about the potency of any anesthetic from its partition coefficient. So if I know the partition coefficient of the compound, I can deduce the potency of it through the Mayer-Overton correlation. My question now, look with me guys about this plot or this line. You will find that increasing of the partition coefficient from 0.1 to 1 to 10 to 100 to 1000 decrease in the potency of the anesthesia. That is opposite to what we said. What we said is that partition coefficient is more lipophilic. So it will be good potency for the anesthesia to pass through the blood-brain barrier, as all here answered. So how Mayer-Overton in their correlation show that more lipophilic is bad in the anesthetic, the potency decrease, and the low partition coefficient give higher potency.
Maybe because the volume of distribution will be increased as well, so it will be more distributed in the cells.
Wrong. Okay. Who's other? Guys, try to think. When we said an easy question, million people answered.
Like if it should be both lipophilic and hydrophilic, no, doctor. So if it is complete lipophilic, it can't absorb the drug, and the like excretion will be high.
Here this is halothane, methoxyfluorine. These have highest lipophilicity. They have about, you can say 990 as their lipophilicity as a partition coefficient.
Maybe because it's gases. So
what, sorry?
Maybe because it's like in the form of, it's like I think it's gas like halogen and no.
No, 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 no. But
No.
what you think is good. All the answer in this area. That here's a partition coefficient between oil and gas, not oil and water. So this meaning what? This meaning the higher partition coefficient is more lipophilic, and the lower partition coefficient is more gases. And more gases is more potent. Why? Because it
Volatile. So it's
as
quick.
inhalation
Okay.
will formulate as inhalation.
Mm.
And inhalation is much shorter in duration of action
Action.
than
Yeah.
injection.
Injection and oral.
Yeah.
Yeah.
Doctor, again, please.
Okay.
Yeah, doctor, I didn't get it.
Okay, please all mute the microphone and will understand me. Here, guys, when we're talking about the partition coefficient in general, we said it is the partition coefficient when we measure between the oil or the lipid or the organic to the water. That's okay. But Mayer Overton not make it for between the oil and water. No, they make it between oil and the gas. Why? Because almost of anesthesia used as injection or inhalation. So he used to say that I will put this as injection and I will put this as, or I will give this as inhalation. So he makes the partition coefficient between the gas and the oily or the organic. So the highest lipophilicity, I will use it as injection, like the halothane, like the methoxyfluorine. All of this I can use as injection. Okay? But when it decreases in the partition coefficient, this meaning that the compound not hydrophilic, no, but more gaseous can present as a gas. And when you say present as a gas, so it can be formulated as inhalation. And inhalation is better than injection for the duration of action, for the onset of action. So the more potent is that gaseous, which is less partition coefficient between oil and gas. You got it, guys?
So,
Got it,
doctor,
guys?
one second, doctor. For gases, the onset of action will be high, the duration will be short, and
Not short, not short, because all of them can induce something in the brain, okay? And when it induces something in the brain, that will make the duration of action. Like that, I can induce inside the brain, we can induce the desensitization of the neurons. So if it make desensitization of the neurons, it will extend it in the duration. Okay, so for example, nitric oxide as onset of action is very, very potent. Okay, and in the duration of action, maybe it is smaller, maybe other is higher, maybe higher, other is less. But here he measure about the potency of the drug, a potency which can be decided about the onset of action. So here we're talking mainly about the onset of action or the potency. Okay?
okay, doctor.
When I ask you guys about the thermal effect about that, if you have a drug and you put it in a soluble form, so if you put it in the flame, okay, this soluble or the solution in the flame will increase the solubility of the drug in the water or not?
Yes.
It depends.
It depends. Some of the drugs may, yeah.
It depends on the reaction between the drug and the water. If the reaction between drug and the water is exothermic, so temperature is not required and it's prevented, and we wish that you put or you make this reaction or you make this solubility in a cold place. For example, if you try to put a piece of sodium in a water, this will leading to explosion because it's exothermic. Okay, when you try to react H2SO4 with, for example, water, this will make explosion. So guys, when you have a reaction with water between the drug and the water is exothermic, you should to avoid temperature. You should to put in a cold place, not a hot place or at a high temperature. So it depends on the compound itself. And if the reaction is endothermic, we require energy, we require temperature to make it. So the temperature, if you put it on the flame, this will increase the solubility of the compound. And that is show why we using the cold bath for babies, for example, for the fever. We using cold bath. What about the cold bath? Cold bath does not contain ice, for example. No, it contains a reaction between, this is the example, if you need to see it. Okay, guys, this is the example that I talking about, the cold bath. Cold bath is what? It's ammonium nitrate dissolved in water. Ammonium nitrate react with water when it is very endothermic. It requires temperature. So if you put the cold bath, which contain ammonium nitrate dissolved in water, on the baby or on the skin of the baby, it will take the temperature of his tissues to react more with the ammonium nitrate with the water. And this is leading to consuming of this temperature and decrease the temperature of the baby. That is the reaction that happened between the ammonium nitrate dissolved in the water and so on. Okay, guys, let's give break for 10 minutes and back to continue. Let's back, guys.
Doctor,
Yes.
please can you explain oil and gas again for partition coefficient?
اوكي. خلينا اقول لك بالعربي. بص يا كنار، انا دلوقتي لو عندي ميه وزيت وبحط الدواء فبيتوزع ما بين الميه والزيت، فمعناه ان هو بيدوب اكتر مثلا في الميه او بيدوب اكتر في الزيت حسب البارتيشن كوفيشن اللي بتطلع لي معايا لغايه كده.
نعم دكتور.
لو انا بقى جيت وقلت انا مش هستخدم الميه، انا هستخدم ان هو توزيعه في الجاز في الهواء، ولا ان هو يبقى في الليبيد اكتر، فانا دوت البارتيشن كوفيشن ما بين ايه؟ ما بين الجاز والليبيد. فمعناها ان لو زاد البارتيشن كوفيشن معناها ان هو لايبوفيليك، يعني بيدوب اكتر في الليبيد. طب لو قل البارتيشن كوفيشن هنا بقى هقول ان هو بيبقى موجود على شكل جاز اكتر، مش هقول ان هو يبقى هيدروفيليك، لا، لان هو ما فيش ميه هنا، في جاز، فيبقى معناه ان هو وجوده اكتر على شكل جاز. طب ما هو الجاز ده انا لما اجي اصنعه في التصنيع بتاعي هستخدمه انهاليشن، هستخدمه كتنفس، يعني بديه كانهاليشن. فالانهاليشن اسرع ان هو يوصل بسرعه جدا للمخ من الانجكشن، فبالتالي بقى انهي الاكتر مور بوتنسي؟ الانهاليشن اكتر من الاويلي او اللي هو موجود على شكل ليبيد. فيبقى ساعتها ان انا ادي حقنه واستنى لغايه لما توصل، ولا ادي انهاليشن على شكل جاز ويوصل بسرعه؟ يبقى مين المور بوتنت؟
يعني راح يكون مور بوتنت. نعم.
Okay, I think that all back.
شكرا دكتور.
You're welcome. Let's continue. Okay, guys. I left this common effect after break because this is somewhat confusing and so on. So let's talking about it. Okay. Please, all focus with me. All focus with me. Okay, guys. I need to explaining in a white sheet here, guys. If we imagine with each other about the following, look with me. I have, for example, the protein. If we imagine this is a protein, this is a protein. What? Who can't hear? Can you hear me, guys?
Yes,
Yes,
doctor.
Doctor.
Yes, we can hear you,
Yes.
doctor.
And can you see what are you
Yes.
writing?
Yeah, protein.
yes, doctor.
Great. Okay. Check your speaker. Maria. Check your speaker, Mariam. Okay. Let's bank. Or let's make what? I will let her go out, then sign in again. مريم. هي فين مريم اصلا؟ هي فين مريم؟ مش موجودة اصلا.
يعني ممكن تكون خرجت ودخلت تخش تاني زي ما حضرتك بتعمل.
Okay. Mariam, can you hear me now? Okay. I will talk now about the salting in, salting out. Look with me, guys. If we imagine this is a protein structure, protein, we know that the protein in water, I think this is Marianne. Sorry, guys. Okay, we say this is a protein and it is soluble now in water. Okay, so we can found what we can found that if you put a salt in a small concentration of a salt, small concentration of a salt, I added it to this, what it will make. So I say again, if I have a protein, now, and there is a water, that's the protein inside the water, it's soluble. And you put a small concentration of salt into this. This will make what? This will make increase solubility of protein in water. Why? Due to salting in. What is the salting in? Salting in that the salt will go in here at the surface of the protein, okay, and help that the water like to dissolve the salt. So the attraction of water will be higher here due to what? Due to presence of a salt. Okay, but if you make the following, let's say another way. If you put the salt, and let's make it in another color. If you put the same salt, but in higher concentration, what will happen? The salt will begin to be far from the protein because it's huge amount. Okay, and this will attract water molecules to the salt because it's ionizable. So protein now has less amount of water. So the protein molecule, look with me, the protein molecule and another molecule of protein will bind with each other by a hydrophobic bonds. Hydrophobic like the pi-pi bond and so on. Okay, this protein and this protein will begin to attract with each other and begin to be huge in the structure, and they begin to be what? Hydrophobic. Because they will attract with each other due to that the water far from the protein to go and dissolve the salt. So the salt attract the water molecules from the protein and let the protein just like the precipitation, like that precipitate. And we call this as a salting out. which mean salting in, that's the salt going to, which is in the protein. But salting out, that's the salt out of the protein and begin to be with each other, attract water molecule and leave protein itself to attract with other protein by a hydrophobic bond and producing hydrophobic molecules of proteins. And that is the technique that used salting out is the major technique when you need to separate protein from fluids. Like if you need to separate protein, like plasma protein from the blood, I can adding a huge amount of salt. This will attract the water molecule to the salt and leave the protein away. So the protein, the plasma protein will precipitate. So I can precipitate the plasma protein from the fluid like the blood through or the plasma through that salting out, adding huge amount of the concentrated salt. And what this phenomena is depend on what? It's depend on Le Chatelier. Le Chatelier, it's something French. Le Chatelier equation or rule, at which when I say, for example, CH3COO, for example, Na plus H2O, this will give CH3 COOH plus NaOH. Okay, when I say this is an equation that acid with base give salt and water. Is it right? Acid with base give salt and water. Is it right? Yes. Le Chatelier said what? Said if you, for example, need to add here, if you add here some of CH3COH or you add NaOH, increase this or increase this, the equation will begin to be predominate to going backward like this, backward. Okay, and that is make what? That is make more solubility. More solubility. Why? Because the water with the sodium acetate will be in ionized form. It will be more soluble. Okay, because this is the salt with the water. Okay, but if you increase the salt, I increase the salt concentration here, begin to increase salt concentration, the equation will shift it here to forward. And this will make what? This will make the water begin to disappear to give what? To give the acid and base. Acid with the base, and the water disappear because the water is here and water disappear in the product here. This meaning that decreasing the water solubility. Decreasing the water solubility. So this is the rule that if you have X plus Y given A plus B, for example, so if you add X or you add Y to this equation, the shifting will be forward. If you add A or add B, the shifting will be backward like this. That's the Le Chatelier rule for the equation. That's when you do something like this, I increase the concentration of the salt. This is leading to the salting out. When you give a small amount of the salt, this will make the salting in. Okay, guys. Okay. Let's go into the other, which is about the dissolution. What is the equation for dissolution? Okay, the dissolution, let's write here, guys, because it is very important. Noise Whitney equation is for dissolution rate, is measures the dissolution. Figs law is used for diffusion. Stokes law used for the friction force, or we can say sedimentation of a compound. The three rules are very important. In exam before, asked which of the following is important for dissolution rate? The Noyes-Whitney equation. Which of the following is used as a diffusion measuring? Figs law. Which of the following can used for the friction force calculation? Stokes law. So guys, if we need to talk about the diffusion firstly, so we have this equation about the diffusion that showing here, if we have, for example, the drug here in this solvent has a concentration 1. It will pass through this membrane, this boundary, the boundary layer, which is a membrane. So it will pass this. This can be called the thickness of the membrane. I can refer to it by delta X, the distance, the thickness. Okay? And it will absorb it to give C2. So now, the difference between C1 and C2, I can call it delta X. And the thickness of the boundary layer, we can call it as a delta X. Okay? And the D is the diffusion coefficient constant. The diffusion coefficient constant. Okay? So I can calculate the J, which is the diffusion rate. The diffusion rate. Okay? So the diffusion of a compound can be measured by the Figs law, which is that the J is minus D delta C, which is the difference between the two concentration, divided by the delta X, which is the thickness or the distance of the boundary layer of the membrane, for example. When I have any drug can enter to the stomach, okay? Any drug can enter to the stomach, okay, like this, okay, as a drug like this. After this, begin to dissolute, begin to dissolute, to be like this in a dissolution form. And after this, absorbed into systemic circulation. Absorbed into the systemic circulation. So we said that dissolution is a rate limiting step for absorption, which means that if there is a dissolution of a compound, there is absorption. If there is no dissolution, there is no absorption. Okay? So guys, what is the importance of the dissolution rate? What that can affecting on what? Can affecting on the onset of action, can affecting on intensity of action, can affecting duration of response, can affecting control the overall bioavailability of the drug form. And that's why we say always that gastric emptying rate is affecting on the drug action. Is it right? Yeah. Because if the gastric emptying is so huge, very, very quick gastric emptying. This means not good dissolution. Okay, so it is bad absorption. If you're given, for example, if you're given a tablet or a capsule for a person with diarrhea, is it like that if he is normal person without diarrhea? No. That in diarrhea, the gastric emptying rate is very huge frequency. Okay, and that's not let the drug stay in the stomach and intestine for longer time to be absorbed well, distributed and absorbed well. That is why that in people with diarrhea, the effect of oral drug will be lower than when there is no diarrhea. Okay. About the intrinsic dissolution. Someone say, doctor, what's the difference between intrinsic dissolution and particulate dissolution? Look with me, guys. If I draw to you like this, for example, a compound like this, and I told you, can you tell me about this compound is more hydrophilic or more lipophilic? So when you're telling me it's more hydrophilic, for example, I say it is easier to dissolute in water. What I explaining now, I explain about intrinsic dissolution, because I give you a structure of the compound and ask you this compound itself is more hydrophilic or less, so it will be easier to soluble in water or not. Till now, I didn't talk about itself. Is it solution? Is a powder? Is a crystalline? Is it amorphous? Is it polymorphic? I didn't talk about this. I talking about the composition, chemical composition, that can say that this intrinsic solubility is good or bad. Okay. After this, I begin to say this is present as a powder that is crystalline. This is crystalline, maybe amorph, maybe raphides, maybe prism, maybe, and so on. So I say this crystalline form of raphides is more better in solubility than crystalline form of prism, for example. So I talking about what? I talking about the same drug, okay, but in a particular form, not as intrinsic. So intrinsic solubility can be determined according to the structure of the compound itself. Okay. And I using always the Noise-Whitney equation to understanding about the dissolution rate, of a compound. Okay. So guys, let's say about this part, about the dissolution rate. Okay. That in the intrinsic dissolution rate is used for what? Is used for evaluate of drug solubility in accordance to the biopharmaceutical classification system, or comparison of different form salt of the same compound, like that. The salt, as we said, the salt structure of potassium of penicillin is higher in solubility and in absorption than benzene salt. Okay, so according to the salt that you will give me, I can decide about the intrinsic solubility will be good or bad. Okay, and the development of the dissolution method. Okay, about the stability of a compound. If the compound in a solid form, I can measure the stability of it through these techniques, that using of the X-ray or the infrared or the spectroscopy, NMR spectroscopy or the Raman spectroscopy, and so on. But about the solution, that it will depend on the temperature, pH, oxygen, light, ionic strength, co-solvency. These factors can affecting on the solution stability. If you put the drug as a solution, you should to do care about the temperature, the pH, the oxygen, the light, the ionic strength, the co-solvency. And I give you example about this. Like what? Look with me, guys. When we talk about the irinotecan as injection that use as anti-cancer. The irinotecan, okay, we can put it as irinotecan HCl, which is a salt of the hydrochloric acid, with a phosphate buffer, which is that a buffer salt, with the water for injection. Okay, that's very good. Okay. When you're preparing this, you shouldn't what? You shouldn't dissolve the campsicine without resorting to heating in the course of production, which means that you should to measure the solubility of the campsicine, which is that the family of irinotecan, tubutecan, which is the plant family. Okay, when you need to extract irinotecan, you should to measure that campsicine, okay, the campsicine solubility or dissolving of the campsicine, and you measure this during temperature, because temperature can affecting on the dissolving of campsicine. So I should to monitor the heating during the dissolving of campsicine to assure that the irinotecan will be stable or unstable in the solution form. It is the same like that when we're talking about chitosan hydrogel. Chitosan used for many things like that, for people needing something for decrease their body weight and so on. It can affect on the liver and so on. Chitosan hydrogel can change reversibly well at different pH ionic strengths, which means that I should to monitor pH and ionic strengths of the solution of chitosan hydrogel. So the temperature, the ionic strengths, the light, the pH, the oxygen, the co-solvency, all of these can affecting on the solution stability, if the solution will become more stable or less stable. In exam, they asked about the chemical characteristics in very easier way, but it is sometimes confusing, makes some confusion for some people. Firstly, what about the oxidation? How the oxidation can occur? By the light. Light and heat can activate the oxygen to be more reactive and to form the free radical that can help in the oxidation of a compound. So what are the functional group having highly susceptible toward oxidation? Alkenes with a double bond, alkenes. Substituted aromatic rings like toluene, phenol, anisols, ethers, thioesters, amines. These are major functional group that has high ability to or high susceptibility towards oxidation. What are factors affecting oxidation? The oxygen concentration, the light, the heavy metal presence, hydrogen and hydroxyl ion, temperature. How to avoid the oxidation or removal of oxidation, and that's the question in exam before. Said what? Said all of the following can used for prevention of oxidation except, and give decreasing the oxygen content. That's correctly, because oxygen presence induce the oxidation. I can using for this antioxidant that stops the oxygen action. Yes, like what? Like oil soluble antioxidant as the alpha tocopherol, lecithin, propyl gallate, hydroquinones, anisols, and water solubles antioxidant like ascorbic acid, the vitamin C, and the thioglycerol and sodium bisulfite and acetylcysteine. All this can be used as a water-soluble antioxidant. Okay, so reducing oxygen content, adding antioxidant, storage in dark and cool condition. Why? Because we said before that light and heat induce oxidation. So you should to store in dark to avoid light. You should to store in a cool place to avoid heat. Okay, all of this. Okay, and addition of chelating agent. Chelating agent, which are these compounds like EDTA, citric acid, tartaric acid, that can complex with bivalent and trivalent cations like iron, like cobalt, like nickel, like these heavy metals can complex with each other, okay, with the EDTA and the cobalt and so on, and that is decreasing the heavy metal action inside the oxidation, because heavy metal can induce oxidation. Adjustment of pH. Yes, I can adjust the pH because the pH can affecting on the oxidation. Because if you have optimum stability of the pH, will reduce the oxidation potential of the system. A changing solvent like what? Like that I change the solvent from a solvent which has higher degree of susceptibility of oxidation, like ethers, like ketones, like aldehydes, that can liberate free radicals and induce the oxidation. I can change the solvent. Okay, and the ones that accept in the exam, all of this can be considered, but except what? Except it said that removal of carbon dioxide from solution. And the big problem that many people answer this question wrong. And when I asked them why you consider removal of carbon dioxide from solution is a good for avoid oxidation, this is not correct. But how you think about this? They begin to say because carbon dioxide is opposite to oxygen in the air pathway. What's this? Okay, because you know that the oxygen is opposite to carbon dioxide, so to decrease the oxidation you remove carbon dioxide. This is wrong. There is no any relation to remove carbon dioxide from solution, so this is decrease the oxidation. This is wrong. Nothing says this. I can remove oxygen from the solution. It's okay. No problem about this. I can remove heavy metal from the solution. It's okay. I can avoid light and heat. It's okay. No problem about this. I can add antioxidant. It's okay. I can optimize the pH to the more stable pH. It's okay. I can change the solution solvent in the solution to lower solvent that has susceptibility to oxidation. I can avoid ethers or alkenes or ketones that has high ability to oxidize. Okay? Okay, guys. What about the hydrolysis, which is another chemical reaction can occur? The hydrolysis. That is what I will say now. One of the most, and you can say power million, okay, important for medicinal chemistry. For medicinal chemistry, which is the devil for almost of people. Okay, when you study, some people found the devil is that the medicinal chemistry. The hydrolysis ranking is lactam has higher hydrolysis susceptibility, then ester, then amide, then imide. Okay, lactam It's come from what? From lactone. This is, look with me, this is lactone ring. If you add here besides the carbonyl group, if you add nitrogen, this has become lactam ring. This is lactam ring. Okay? When I say the ester, ester is R C O O R dash. When I say amide, R C O N H2. When I say imide, who know about imide? R C O N H C O R dash, which means that the NH have CO before and after. CO before it and after it. That's called imide. Okay? Look with me, guys. That is high susceptibility to hydrolysis. What's the meaning of hydrolysis? That
Doctor, can you write it up, imide?
Okay. Okay, amide is R C O N H C O R dash, which means that NH at the middle and beside it CO and beside it CO from the both sides. Okay, that's imide. Okay, so let's say that the susceptibility for the hydrolysis is meaning what? That adding the water molecule OH and H, so break down to add H here and OH here, it become like this, COOH, and here is NH2. Is that right? Yes. And the breakdown of this. So this is open the lactam ring. This can open the lactam ring. Okay. And the hydrolysis here is that breakdown of the ester bond to add here OH and here H, water molecule. Okay. To give what? To give the acid RCOOH and the alcohol ROH. And here is that adding the OH here and H here. Always OH going to the CO. Okay, so it become acid, carboxylic acid, RCOOH, carboxylic acid, and NH3, which is the this is NH3, ammonia. And this is here that the hydrolysis occur in 2 steps. Hydrolysis to release amide plus the carboxylic acid. Then the amide will dissolve again by hydrolysis to give the amine plus carboxylic acid. So the amide can be hydrolyzed in 2 steps. So we will found the lactam is the easiest to hydrolyze. Then ester, then amide, then imide. What's the importance, doctor? How it present in exam? That I can write down like this, look with me, and it present in exam before like this. C H 3 and here CH 3 CO O CH 2 and write down here C2H5 CH3 CO and HCH OH like this, and give you other figures or other compounds, but let's compare between 1 and 2. Ask you in the exam, which of the following is the longer duration of action, 1 or 2?
2.
Excellent. Why?
Because it's not gonna hydrolyze easy. Like one, it will like it's faster to be hydrolyzed.
Why?
But two, because two is it's, I guess, 1 second. It's amide
Amide.
and amide, yes, and one it's ester.
Ester. Excellent. How you know about this? The hydrolysis or the breakdown of the ester is easier than amide from this, from what we say now. That hydrolysis always in a chemical reaction, that hydrolysis is easier for ester than amide. So when I talk about that, which has a longer duration of action, so number 2 will be longer duration of action than number 1. Why? Because the hydrolysis for CONH is difficult than in the ester. So the ester can be hydrolyzed first. After this, the hydrolysis come for the amide. So this meaning that the amide will stay longer duration inside our body than the ester, which has a longer duration of action. Okay, guys. When we consider that hydrolysis, how to avoid hydrolysis? By a changing of the pH, yeah, to make it pH adjustment to be more stable, and addition of a surfactant like non-ionic, cationic, anionic surfactant, stabilized drug against base catalyst. Base, which I mean by this, for example, the ointment base or cream base and so on. Salt esters, okay, like clindamycin. Let's imagine about that clindamycin that it can be hydrolyzed by enzyme. Hydrolase enzyme, okay, can make hydrolysis of clindamycin. How to avoid this? You can make salt ester. What the meaning of this? Look with me. If you, this will destroy the clindamycin. If the hydrolysis enzyme come, it will destroy the clindamycin, metabolize the clindamycin. So it will not be effective. So how to avoid this? By the following. Look with me, guys, that I will do the following. I will adding a phosphate ester. Phosphate ester, COOB. Okay, what happened? The hydrolase enzyme will consumed to destroy the ester bond between the phosphate and the clindamycin. This will liberate free clindamycin that give the action, pharmacological action. So I avoid that destruction of clindamycin by make salt ester, like phosphate ester. So the all hydrolase enzyme will consumed to destroy the bond between the clindamycin and the phosphate ester. They will consume the time to destroy the ester bond. That is will help that liberation of clindamycin as it is, okay, as a free to give the action. So I avoided the destruction of clindamycin by the hydrolase enzymes. Okay. I can use desiccant that we said that can absorb the moisture from around environment, and can using complexing agent. Okay, so this is about the hydrolysis. What other? We have a photolysis. A photolysis. We just said, guys, that the electron or energy can come from the photons, the light. So we should to avoid the light action on some of compounds. And here I try to bring the most common in the market. 3 or 4 example as a maximum for each. Like that, in dealkylation is a way of light action that, for example, I have in the diphenhydramine, the chloroquine, the methotrexate. I have what? I have, for example, the compound that contain nitrogen and contain here CH3 on the nitrogen, or C2H5 on the nitrogen, which mean alkyl group on the nitrogen. That the dealkylation, that removal of this alkyl group from the nitrogen, okay, is called N-dealkylation. Can be occurred by the light. The light can give energy to remove this group from the nitrogen, and that is can make degradation of the compound, which means that the diphenhydramine, chloroquine, methotrexate shouldn't expose to light. The dehalogenation, like the chlorobromide and the furosemide, that containing, for example, the fluor, or containing chlor and containing so on, that is, and like the cebrofloxacin, which contain fluor, also can have dehalogenation. The halogen, fluor, chlor, brom, iod, can be removed from the compound, and that's leading to problem of the drug. Like that, dehydrogenation of calcium channel blockers. You can find nifedipine, which is a calcium channel blocker. Okay, can loss of water from the solution, and this leading to changing from yellow color to brown. So if I found on the over the counter or on the shelf, I found that the nifedipine solution, it changed from yellow to brown. This meaning it is decomposed, and I can't give to a consumer. Okay. And when we're talking about the decarboxylation of the anti-inflammatory drugs like naproxen, like fluorobiprofen, like the benzoxaprofen, and oxidation for chlorobromazine or phenothiazine that contain nitrogen or sulfur, isomerization or cyclization of the noradrenaline or doxepin, rearrangement like metronidazole can give oxydiazine, which is yellow color. So if you have the metronidazole, which is a white in color, it changed it to yellow in color, this is also meaning that it decomposed by the light and I can't use it. Okay. So guys, let's say that the photo decomposition, how to avoid it, how to prevent it, by using suitable packaging, okay, that prevent us from the UV light absorption, okay, and some of the IR absorption and so on, using of antioxidant. Why antioxidant, doctor? Because we just said that photons or the light can induce the oxidation of the compound, and protection of drug from the light, like nifedipine, I should to manufacture it under the soda light, the sodium light, okay, and the avoiding some paths like sparfloxacin, one of the common drugs in the market, sparfloxacin. You shouldn't use it in your skin and after this going outside the home in the sun. Okay, like that. Sometimes you found some cosmetics say day and night, that you should to use this cream at day and use this at night. Why? Because this cream of the night has a photosensitivity. I can't use it and going outside in the sun, okay, to absorb the UV light and destroy, and maybe leading to skin reactions and inflammation. Okay, photostabilizers used like the colorant curcumin, azorubine, and pigments like iron oxide and titanium oxide. Titanium oxide is one of the most common pigments that used in the cosmetics. And the coating agent, which is a pigment like titanium oxide or zinc oxide, I can using it. Other ways of them avoiding that in the chemical reactions and so on, the racemization of the epinephrine, the L form and D form. L form is more potent, which is a 15 to 20 times potent than D form. Polymerization, like the darkening of glucose solution. When you have a glucose solution, or 50% dextrose, for example, and you found that this clear solution, you found it become to be damper, become to be darkening. This meaning that it is have a decomposition now due to the polymerization, that this compound polymer I shouldn't give to the patient, because this meaning that I will put inside the patient vein, I will put more viscous, because polymerization meaning more viscous compound. Look like that when you look at water and put inside it 1 or 2 teaspoonful of sugar and stirring, okay, you can see the sugar inside. But if you put about 30 teaspoonful of sugar and begin to stirring, you will find that it become more viscous due to polymerization here. Okay, isomerization like that, the tetracycline, it's very, very important example. Tetracycline about this. Tetracycline is very important example to understand about that it can isomerize, and this isomerization can leading to many problems. And the reversible isomerization can become under the pH of 2 to 6, but otherwise it will be irreversible tetracycline isomerization, which means that I can found the tetracycline in between 2 to 6 pH of 2 to 6, the change can be reversible, but outside 6 over than 6 or less than 2, I can found this is irreversible. And let me say that tetracycline isomerization, guys, leading to toxic metabolites, toxic drugs. And that's why when you have a tetracycline close to the date of expiry, you should to avoid it to give to the patient, because the tetracycline, if it changed, if it is isomerized, can leading to very bad toxicity till death. Okay, decarboxylation can be occur for the anti-inflammatory drugs. Almost of anti-inflammatory drugs can be decarboxylated and so on. Enzyme decomposition, for example, enzyme decomposition is very, very important in case of buccal tablets and prodrugs. Like that, buccal tablet will stay in the buccal, in the mouth for longer time. So you should to avoid that the saliva and these exudates or these fluids inside your mouth contain many enzymes. You should to avoid the enzyme decomposition of the buccal tablet. And you should avoid the L-dopa to metabolize as a prodrug by adding carbidopa to it, which is the brand name Senmet for the Parkinsonism. Okay, guys? Okay. I finished about the pharmaceutics and I send you the dosage forms that you should to keep with heart of study. Keep with heart of study. Because in the exam, he will ask you like that, which of the following is a glidant, which of the following is lubricant, which is the following is filler, which of the following is a disadvantage of emulsion, which of the following is advantage of, for example, ointment, about the ointment base, which is that water or hydrophilic base, and which is hydrophobic base, which is about the method of the litigation,
Doctor,
and so on. Yeah.
can you explain hydrophilic and hydrophobic? I mean, how we can know this is hydrophilic or hydrophobic from the functional group?
What's the meaning of the function group? I can't understand.
I mean, how we know this is hydrophilic or hydrophobic when we see the structure?
When you look at the structure, you talk about something far from what I talking. Is it right? Because I said hydrophilic and the hydrophobic base is something.
No, it's not about only today. I mean, in general.
Yeah. Okay. About that, what you asking about, which is that hydrophilic group and the hydrophobic group, always the hydrophilic group can producing H bond or a polar action, like that OH, COH, NH2, all of this hydrophilic. But hydrophobic, which like that hydrocarbons, given hydrocarbons, I increase the hydrocarbons, I increase the resonance, I put aromatic ring instead of that, just like that hydrocarbon. All of this can increase the lipophilicity. That's in general. Okay. So the that's about the which can producing ionized form, which can producing hydrogen bond, is more hydrophilic. Like that, when I say, for example, to let you understand, when I say OH, OH can producing with water hydrogen bond here. So it will be more hydrophilic. Okay. When I say, for example, that, for example, COOH, so H, which means that this hydrogen, when it can be out and this give negative, okay, so this is more ionizable. So at this moment, I can say this is more easier to be soluble in the water. When I say about, for example, the function group RCO OR dash, it is bad solubility in water. Why? Because here here it is a hydrocarbon and here is a hydrocarbon. Between them, that COO, so there is no any about the H, which can producing a hydrogen bond, and there is no any about that break given that ionizable form. So the ester here is more lipophilic than alcohol, for example, because alcohol contain OH. So alcohol is more hydrophilic. Aldehyde is more hydrophilic, but the ester is more lipophilic. You got it now?
Yes, doctor. Yes.
Okay. Okay, guys. So I need you to study well about this, guys, and we have a lecture for management next time. So you should to try to study everything about pharmaceutics that we give, because next time I will explaining about biopharmaceutics, about some points in materials that you had, which is about the emulsion as a colloidal system, zeta potential. I will explaining about the sterilization, this amount, these parts, and after this we will give him pharmacokinetic, pharmacodynamic, and after this exam. Okay, there will be exam about what we give till now, from the beginning till now, from the
From
beginning,
the early beginning.
from the beginning. Yes.
Wow.
Yeah.
Okay. Okay. So, doctor, after the pharmacokinetics and after this exam, like that's it, we're done, or we still have some more to explain? Like we still have more.
Give CVS. You didn't give the CNS.
Oh, so the last part for the organs, like
I just say that we, after this, we will have to given the CVS, the CNS, autocoids, the three major topics, and after this we will give calculations after this. So the previous part, if you studied very well, these topics will not consuming too much from us, and after this we will start our revision.
okay,
So,
awesome.
so try to study from now, guys. Try to review about the previous, because I will give so soon exam about everything. And when I say everything, it will be everything, everything medical. I will not tell you about the management, because after this I will give exam for management alone, not for not connected with medical, to let you study this alone, this alone. Okay, so try to study and do your best, because so soon there is an exam about medical part. Okay, guys, have a nice day, guys. Bye-bye.